Alright, today we're going to change polar representations into complex numbers. So let's remember what a complex number is. It's in the form of z equals a plus bi, where a and b are real numbers and I is the imaginary unit, defined by I equals the square root of -1. Now a is the real part of z, denoted as re-z, so like the element of the real, while the number b is called the imaginary part of z, so denoted imz, so the element of the imaginary. So when we graph a complex number, we can do it in the order of a comma b, where of course our coordinate grid is the imaginary axis and the real axis. So the real axis like our x and imaginary axis like our y. So just like a coordinate plane. Since the order pair AB gives the rectangular coordinates associated with the complex z equals a plus bi, the expression z equals a plus bi is the rectangular form. So if we have any questions that are asking for rectangular form, we are looking for the answer to be z equals a plus bi. Okay, but we can also associate it with polar coordinates. So we have r equals theta. So we need to look, we're going to convert where we can write this in polar coordinate form. Okay. Now, let's go to the modulus and argument of complex numbers. So, if we have z equaling a plus bi as a complex number, a is our real element and b is our imaginary element, we have r comma theta being polar representations of the point on the rectangular coordinate a comma b. So, modulus, right, which also has been said magnitude. That is represented by our r, but r has to be positive, so it's the absolute value of z. Okay, this is what we're going to denote that as. The angle theta is an argument of z, so the set of all arguments of z is denoted as argument element z. Now, keep this in mind that this is a lowercase. So the lowercase argument considers all thetas. Whereas if we were just considering negative pi to pi, then theta is a principal argument. And in that case, we have our capital A. Alright, now down below it says quick check for the unit circle, but let's not focus on that right now. Let's just go forth. In example 1 here, for each of the following complex numbers, we're going to find the real element, the imaginary element, the modulus, and then the arguments. So for A here, we see that the real element here is a, which in this case would be the square root of 3. The imaginary element is going to be b, which in this case is -1. So let's keep this in mind that z equals a plus bi. Alright, so if you go back to the other page, the modulus, and I'm going to write this just this one time because we should know this already, that the modulus is the same thing as the r squared equals x squared plus y squared. Think of this. R is our radius, that's where we get it, right? And actually it's r. Okay, there we go. If we want r comes from the radius that we could find from an x, y coordinate, right, doing our right triangle. So that's where we get this. But in this case, of course, this is going to be a squared plus b squared. Alright, now, if we were to actually place the square root of 3 in and -1, we would end up with r equaling plus or minus 2. But we know that r has to be positive, so our modulus is 2. Okay, it looks like we're running out of room, so let me circle what we needed for answers so far. So the modulus, our imaginary element, and our real element. So let's do our arguments on the side. Well, when it comes to arguments, guys, we need to remember what quadrant we're in. So if you look at this being the coordinate square root of 3, -1, that means we are in quadrant 4. And if you remember that to find theta, it's tangent theta equals b over a, which if we do this outright, then we have tangent theta equals -1 square root of 3. Alright, so when we do this, we find that theta will equal a -pi/6. And then we're talking about every argument. So we're looking at plus 2 pi k, k being an integer. Okay, so this is our argument with the lowercase of z, because that is every situation. But if we wanted to know particularly the argument of z, the element z there, that was specific between -pi to pi, the only value we would get there is -pi/6. Now, because I just went over the way to find theta and to find r, I'm going to do this a little quicker so I can save space too. So for b here, our real element is going to be -2. Our imaginary element is going to be 4. Now our modulus, well, when we do our r squared equals a squared plus b squared, and we actually solve for that, we should get a +2 square root of 5. Again, if you need to, pause right now, solve for that, and see if you get the right answer. Now, if you look here, we are in quadrant 2. Alright, so when we think of this, and we get tangent theta of 4 over -2, which is not one of our special numbers, right? So if we go back to chapters, we have to remember that in the second quadrant, we would get theta equals pi plus arctangent of that number, which in this case is -2. Now, it keeps going around and around and around, so we have plus 2 pi k, for k being any integer. So this would be our argument of element, right, with the lowercase. But if we were talking about our specific argument, we would get pi plus arc tangent of -2. Alright, C. Z equals 3i. Well, keep in mind that this is 0 plus 3i. So our real element is 0. Our imaginary element is 3. Our modulus then would come out to 3 also. And now if we talk about where this is going to be, well, think of it on a graph, right? If we go 0, 3, where are we? We are right on that axis right there. So our theta is going to be pi over 2 plus 2 pi k, for k is any integer. And of course, that is our argument Now, if we want our specific argument, you would just get pi over 2. Okay. Now, and this one, as you can see, if we put this out, we get negative 117 plus 0i. So that means our real element is negative 117. Our imaginary element equals 0. So our modulus ends up being positive 117. Alright, let's look at where this is. That's over here, right on that axis. So that means that theta equals pi, 'cause that's where we're at, plus 2 pi k, for k being any integer, and of course that is our argument element. But if we want our specific argument, we would just have pi. Alright, let's review some of these properties. So these are, we're just going to go through some of these. We have to keep this in mind. So the modulus is the distance from C to 0, just like our R if we pictured it that way. The modulus is going to be greater than or equal to 0. Think of that. That makes sense because distance is always a positive number. Okay. Now we were talking about that the modulus pretty much is the square root of a squared plus b squared. Okay. But think of it, A is the real part and B is the imaginary, and that's where that comes into play. What we find also is that some of these rules stand. If we have Z times W, it's the same thing. Okay, so this is 2 modulus, guys. If we were doing Z to the n, we could do a power rule there, and their quotient stays the same. But of course, W in this case cannot be 0 because we can't divide by 0. So let's look at the argument. Okay, so the real part, if the real part is not equal to 0 and theta is in the argument, then tangent is the imaginary over the real, which makes sense because it's B over A. If the real is 0 and the imaginary is greater than 0, then the argument is in this stance. So pi over 2 plus 2 pi k. We actually went through that one, right? Whereas if the real is 0 and the imaginary is less than 0, then we have negative 2 pi k. And that makes sense, right? Because this second one here would be ending up right there. This third one would be down here on this axis. Okay, so if the real equals the imaginary and equals 0, then our argument is between negative infinity and infinity because it would be the origin pretty much. Alright, polar form for complex numbers. So what we want to do is make sure that we're linking everything together. So I like this graph here because it pulls everything together. So here we have a comma b, which is our rectangular pretty much. But we can also rewrite that in complex form, which then we look at the polar form. Okay. Then we think of our r for a radius in polar, but our modulus for our complex. Okay, and then we have our theta. Alright, so let's make sense of this. In section 8.1, we learned that A is r cosine theta and B is r sine theta. Making these substitutions, right? We can actually substitute this into our complex numbers. Okay, so instead of just A here, we're going to put r cosine theta plus r sine I. So sometimes we put the I in front of sine just so we know that the I is not with theta, it's with sine theta. Okay, so just be careful of that. Now, we also did in 8.1, how we factored out the r. Okay, so we factored out the r here, and this is what we get. Well, to even write this simpler, many books will say r cis, but the cis is just all of this. Okay, so we're going to have to go back and forth. Just keep in mind that cis is the shorter way of writing this out. Okay, so a polar form of a complex number. Suppose z is a complex number and theta is within the argument of z. The expression modulus 6 theta is modulus times cosine theta plus I sine theta. So see how they put the I in front there. Is called the polar form of z. So this is what we have to remember, that when we're talking about complex numbers, this is the polar form right here. Okay, so we are going to do some of that now. So let me rewrite this out. And for A, I'm going to go step by step, but then I'm going to go faster for B and so on. So this means 4 times cosine 2 pi over 3 plus I sine 2 pi over 3. Okay, now we can use our unit circle. We get z equals 4 times -1/2 plus I square root of 3 over 2. Let's distribute that 4 out. We get z equals -2 plus 2I square root of 3. Now, of course, in the directions it says find the real element and the imaginary element. So the real element here is -2, and the imaginary is 2 square root of 3. Now, I'm going to do these faster in the sense that I might not show this unit circle part, guys, okay? I'm going to separate it and then go right into multiplying that modulus out. Okay, so in B, this is saying that 2 times cosine of -3 pi over 4 plus I sine -3 pi over 4. Okay, do your unit circle, all that stuff, distribute out that 2. You get negative square root of 2 minus I square root of 2, which then means we find that the real element equals negative square root of 2, and the imaginary element is negative square root of 2. Alright, one more page, guys. Let me put this down underneath. Alright, so C here, we have 3 times cosine of 0 plus I sine of 0. We distribute all that out, we get 3. So the real element is 3. Sorry, guys. And the imaginary element is 0. Oh, it's a little bit easier, right, guys? So here, let's do this. So our z or our r is 1, guys. So we're just going to have 1 times cosine pi over 2 plus I sine pi over 2. That's really nice too. And we get just I, which tells me that the real element is 0 and the imaginary element is 1. Just keep in mind the imaginary does not include I, guys. It's a coefficient that goes with it. Alright, so that was going from our polar to our imaginary. Now we're going to go back. We're going to find the polar for these, and I said imaginary, but I meant complex. We're going to find the polar from these complex numbers. So we're going to go backwards here. So for A, we have to keep in mind that we want, because we want our final answer to be the cis, okay? So we need the r in front and we need our theta. Well, how do we find these things? If you remember, to find the r is the modulus, okay? So if we did our square root of a squared plus b squared, in this case we would get that our modulus, or our r, is 2. Okay, theta. Well, let's keep in mind we're in quadrant 4. Okay, and we have tangent of theta equals that negative 1 over square root of 3, and we found that earlier, right? That was our negative pi over 6. Now, by the way, guys, when we do this polar form and everything, we're going to stay between negative pi to pi. So we're not going to do that overall argument. We're going to do that specific argument. So theta equals negative pi over 6. So our final answer is going to be z equals 2 cis negative pi over 6. Okay, now for B, alright, for B here, we want to keep in mind, okay, let's say the modulus, okay, which is again our r. So we get, we did this a squared plus b squared and the square root of that. Now don't forget, we'll keep in mind that r has to be positive, so we get 2 square root of 5. Okay, let's look for theta. So we're in quadrant 2, and we have that if we do our tangent of theta, right, we get our negative 2 again. Now what we had put down earlier, of course, is that theta then will equal pi plus arc tangent of negative 2. But I want to show you guys this another way also, because some people write it. Remember, we have that property that arc tangent of a negative number is the same thing as switching it to minus arc tangent of the positive of that number. Okay, guys, so that's theta. So when we write it in the form of our polar form, we're going to get that z equals 2 square root of 5 cis, because it's just putting it together, remember, of this pi minus arc tangent 2. Alright, 2 more questions, guys. Now, C and D are going to be a little bit more easier to see. Let's look at this. So, we have our modulus, which is our r. So, our r equals 3 because it's positive. And then, of course, we don't have to think of this, right? Because 3i would be right down here. And we are at theta equals pi over 2. So our answer for z equals 3 cis pi over 2. That one was pretty easy, right? And then for D, again, we have our modulus that equals 117 because of positive. Now if we think of this, if we were to graph it, we were over here. And what rating we were at? We were at pi. So theta equals pi, and our final answer being z equals 117 cis pi. Oops.